Welcome everyone. Uh, Welcome back to Fundamental of Econometrics. I'm going to start the lectures of week 10. I hope you have a pleasant break after the midterm. Let me link the previous course content with the course which we have to cover in the post-mid period of the semester. So the semester was started with the introduction and revision of statistics, two concepts which you have already covered in your mid-course, post-mid course in the Statistic 2 course. In the first week, it was basically concentrated on the concept of Statistics 2. In week 2, the course was focused on the linear regression model, mainly the theory part. We did discuss the linear regression model, the nature and the sources of data, the internal source, the external source. Then we did discuss the estimation of the linear regression model. In week 3, we moved to the classical linear regression model. We discussed its assumptions, which I'm going to discuss today again. And then we talked the theory about hypothesis testing, the R-square, the fitness, the goodness of fit of the estimated regression model, and then an example that how we can use all these concepts using the regression analysis. From week 4 and onward, we moved to lab sessions, and we started with, in week 4, the functional form of regression model, in which we started with discussing the interpretation of log, linear, double log, or constant elasticity models, followed by the testing the validity of linear restrictions in the regression model. So that was week 4. In week 5, we learn how we can interpret the coefficient associated with log linear, log lin log, or reciprocal models. We learn what are these models and how these models can be interpreted when we estimate. I hope all these terms and jargons, technical ones which I'm using, is making perfect sense to you. In case you have any problem with getting any of these terms, I would strongly advise you to go to that particular week and go through that content which I have shared with you, or listen the recording of the lectures, because whatever we are going to study from now onward, it's going to be linked with what we have studied already. So in week 6, we move to discussion of polynomial regressions, the choice of the functional form of the regression, comparing linear and log linear models, regression on standardized variables, and measure of goodness of fit. In polynomial regression, we did talked about that how we can use a higher power regression model rather than just using the linear single power explanatory variable. Then we move to the choice of the functional form, like whether we are going to go for the linear modeling or non-linear modeling, and then comparing the results and then picking the best out of it. We also talked about if we use the standardized form of regression. If we use the standardized form of variables in a regression model rather than using its original form, that how our regression analysis will work. Finally, we move to measuring of goodness of fit of a regression model. In week 7 and week 8, we were focused on use of dummy variables in the regression models. We started with the concept of dummy variable, what it means, and the interactive terms associated with being created from dummy variables, which were of two types: the interactive dummy and the differential dummy. Interactive dummy affect the intercepts, and the differential dummies affect the slope of the regression line. And then we learn how we can use the dummy variable in structural change measurement and seasonal data. And finally, we use a SAIL function to apply these concepts. So this was a quick overview of what we have studied in the last 8 weeks. Now, before starting today's lecture, let me link all these concepts or these blocks which I have shared with you with what we are going to study. So let me give you the link with the what we are going to study next. So we started with the basic statistics concept. We move to econometric theory, how we are building economic model, econometric model. Then we move to estimating these models, so estimation of the regression model, and in these we learn from where we are going to get the data, how we are going to test the hypothesis using T and F statistic, how we are going to look into the model fit info, the F statistic, the R square and the T value, and then the formulation, estimation and interpretation of model. Now focus on that: formulation, estimation and interpretation of the model. Formulation refers to defining economic model in which we identify the different dependent, the explanatory variable and the dependent variable and its functional form. Then we go for the estimation part, which is the econometric model. So econometric modeling, that's the second one, econometric model. So we go for the estimation of it, and then the interpretation. Once you formulate it, once you estimate it, then the next step comes in the estimation, like the interpretation, like that's the most important one. So we spent 3 weeks of discussing that different kind of models, like log, lin log or double log models, how to interpret the coefficients of all these variables. Then finally we talked about the dummy variables in week 7 and week 8. So this was the course we covered. Now what's next? Let me focus on estimation of the regression model. Estimation of the regression model was, as you can recall, was done through ordinary least square method or OLS method. So you should remember that there were number of assumptions based on which the OLS method was applied. I hope you can recall some of that. For example, the error term is having zero mean. The successive value of the error terms are not correlated, which we call the autocorrelation. And similarly, multicollinearity, the problem of multicollinearity or some others, we did discuss that assumption. I'm not going to mentioning every assumption right now because it's on the next slide. So let me make my point. So the assumption of OLS was the foundation which were required to apply the ordinary least square method. So these assumptions were important. Now what's next? Next is we are going to see what happens if multicollinearity is there in our data and we apply ordinary least square method to a data to estimate a regression model. So let me put it more formally or straightforward. We have a data, we want to make economic model out of it, then econometric model out of it, and then finally we want to estimate that model. But the problem with the data is that it has a problem of multicollinearity. So now how we gonna check that how multicollinearity is going to affect over this analysis? So in simple word, now we have to repeat all these things or all these concepts and check that how multicollinearity is going to affect what we have been doing earlier. We are going to see that how our estimation, our analysis is being influenced by multicollinearity. So that's the topic of week 10. In next week, we are going to see again how heteroscedasticity is affecting our OLS method. That's the next 2 weeks. And then autocorrelation is again in next 2 weeks, in which we are going to see if there is autocorrelation in our data, what happens to OLS assumption. Assumption obviously get violated, and then what happens to the process of ordinary least square method and the estimation of our regression model. So these 5 weeks which we are going to work on is in these next 5 weeks we are going to discuss the 3 assumption of OLS, how it gets violated, what it is to start with, what happens if it gets violated. It's kind of like what are the consequences on our estimation process. Then how we can find it. Then how we can fix it. So these are few things which we are going to study in the next few weeks. What's next after studying these three blocks: multicollinearity, heteroscedasticity, and autocorrelation? Well, the next one is then we are going to study two more topics in week 15 and 16, and these are regression model with cross-sectional data and topics in time series econometrics. These are the other two topics which we are going to study in next 2 weeks. So this is a complete course overview of our basic econometrics course, and perhaps this one slide can betterly summarize the entire course which we have covered and what we have to cover in the upcoming weeks till the final exams. So let me move to now the course of week 10. In week 10, if you look into the block, it's chapter 4 of the econometrics by example by Gujarati, and the topics which we have to cover is more or less the entire chapter of the book. The chapter book is the critical evaluation of classical linear regression model, and it's the multicollinearity is the main topic. We are going to talk about the consequences of imperfect multicollinearity. Then we are going to see an example. We are going to see, as I told you earlier, that how we can identify the existing of multicollinearity in our data, the remedial measures which we can take, and then there is a method which is called principal components analysis, which we are going to study as well. So before starting the formal content of this chapter, it's from my side, it's highly recommended that we first discuss the multicollinearity by itself, the concept of multicollinearity, and then we go for discussing the topics of this book. So let me start chapter 4, the regression diagnostic multicollinearity. So let me start with the background, the concept of multicollinearity. Now I'm going to start from week 3 slides, and these are the slides of the classical linear regression model assumption. Here I'm not going to discuss these assumptions in detail. For detail, it's better that you go to week 3 slides and lecture 5 or lecture 6, in which we discussed in very much detail these assumptions. Here I'm going to just display the assumption, and if you see, there are 7 assumptions of classical linear regression model, A1 till A7, and if I quickly go through it, the first assumption says that the linear model the model should be linear in parameter. The model which we want to estimate, the regression model which we are going to formulate, which we are going to estimate through ordinary least square method, it requires that the model should be linear in parameter. That's the first requirement of the ordinary least square method. Then we have to see the regressors are fixed or non-stochastic. Now what does it mean? I can explain it again, but it's not the right time. We already did that. So if you can't get that, go back to lecture number 5 and 6. Then expected value of explanatory variable, the expected value of the error term, given that explanatory variable x is 0. Then the 3 homoscedasticity, autocorrelation, and multicollinearity. These are the 3 major assumptions, and the next few weeks course is based on these 3 assumptions. So again, I will refer you to go back to that video if you are not getting what is meant by homoscedasticity or no autocorrelation or no multicollinearity, and then finally no specification bias. So in this chapter, we are going to focus on non-multicollinearity or no perfect linear relation among the x variable. So since this is the chapter, so I'm going to explain this in detail. No multicollinearity in very simple word mean that when you are modeling a data and you have one dependent variable and 2 independent variable. Now this assumption requires that the two explanatory or independent variables should not be perfectly correlated with one another in order to have the classical linear regression assumptions being met. Or in other words, for classical linear regression model, OLS assumption would not be violated if there is no perfect correlation among the explanatory variable. Now, let me go to more formal way of putting it. So, one of the assumptions of the classical linear regression model is that there is no exact relation among the regressor or the explanatory variable. And if this assumption violate, we say that we have the problem of multicollinearity. Now, there can be a case when we have one or sometimes we have more than one such relationship among the regressor. So we call it a multicollinearity or collinearity. So when there is one relation between two explanatory variables, we call it collinearity. When there are more than one linear correlation among the explanatory variable, we call it multicollinearity. So let me put it more simply. Let's say we have 10 explanatory variables in our regression model. So if there is only two variables which are correlated with one another perfectly, so we call it collinearity. It's like just two variables formulating just one relation, so we call it collinearity. And then if there is more than two variables being formulating more than one such relation means linear perfect correlation, so then we call it the case of multicollinearity. But for this chapter and this course, we are going to use collinearity and multicollinearity as interchangeably, and we will just call it multicollinearity irrespective of if it's just two variables being correlated or more than two variables being correlated in the regression model. So there are two types of collinearity. One is called perfect collinearity. In perfect collinearity, a perfect linear relation between the two variables exists. So what does it mean? First of all, you need to know what's meaning by correlation. Correlation means the co-moments of two variables. So when the two variables are perfectly moving together, either in same direction or in opposite direction, we call it perfect collinearity. So when such situation exists, we call it a case of perfect collinearity. And then the second one is imperfect collinearity. The regressors are highly correlated but not perfect. Now, this is different than the perfect collinearity. In perfect, when one variable moves, let's say one variable increase by 10%, the other will increase by 10% or decrease by 10%. So that's the case of perfect collinearity. But we may have a case when one variable is increased by 10%, the other may increase by say 5% or 3% or 8%. So we call it a case of imperfect collinearity. Or we can say one variable increased by 10%, the other decrease by 9%, by 8%, or by 6%, but less than 10%. So we call it a case of imperfect multicollinearity or imperfect collinearity. Now, why we are making the distinction between perfect and imperfect collinearity? The reasons for that is when there is a case of perfect collinearity, the OLS method breakdown, you are not able to estimate a regression model if there is a case of perfect collinearity. And if there is a case of imperfect collinearity, you are able to estimate the model, but it has the consequences. So let me go there and let me show you what are the consequences of multicollinearity. That will explain more the point I have just placed or argument I have just placed. So consequences of multicollinearity. So as I told you, if there is a perfect collinearity among the explanatory variable, OLS estimator cannot be estimated. So why we can't do that? For that, I have to link you to assumption of OLS method. So the statement of multicollinearity says that there is no perfect linear relation among the x variable. So let's say X variables refers to all the explanatory variable in the regression model. So let's say we have two variables X and Z, and they are perfect collinear. So in that case, the two variable would be perfectly like if you know one variable, you can perfectly say about something about the other variable as well, or you can determine fully the values of the second variable. Let me put this argument in some example, concrete example that will make more sense to you. By the way, this slide was discussed in our previous lecture, which I was referring earlier. So let me start with the dependent variable income, and then I'm going to regress this income on age, but I'm measuring age with age in months and age in years. Now you can clearly identify that age in months and age in year are two variables, but both these two variables is perfectly determined from one another, or in another word, it's like perfectly correlated with one another. So if I write a model and I estimate this model, income being regressed on age in month with a coefficient of beta 2 and age in year with a coefficient of beta 3 and B1 and error term being added to it. So now focus on the interpretation of this model. If we focus on the interpretation of the coefficient B3, what does B3 says? B3 says that if age increased by 1 year, income would increase by B3, keeping age in month constant. Once again, age in year, B3 shows 1 unit increase in age. So 1 unit increase in age is age increase by 1 year. What happens to income? That's B3, but keeping age in month constant. But the question is it possible to increase age by 1 year but keeping age in month constant? Technically, it's not possible. So let me demonstrate you how this will break down the OLS method. So formulas for multiple linear regression model, again, I'm referring to the old slides. If I start with the multiple regression model in which we have two explanatory variable x2, x3, you can think of the same example which I showed you a while ago. X2 could be age in months and x3 could be age in years. So you can keep that in mind, or you can just think of a random model in which we have two explanatory variables. And we already learned that if we apply OLS, we can estimate this regression model, and we could have yi estimated value being equal to beta 1. That's the estimated value. So the small b refers to the estimated value of the coefficient b1, and then we have b2, that's the estimated value of the coefficient b2, and then we have b3, that's the estimated value of the coefficient b3. So now how we got the value of beta 1, beta 2 or beta 3? I already show you when you apply OLS to a multiple regression model, you apply the minimizing error sum of square and you can derive the mathematical formula, and I believe you use that in your statistics 2 course. Let me show you that formulas as well. If you want to estimate B1 from your data, all you have to do is you have to take the mean of the dependent variable and then minus B2. B2 is equal to another formula from where you can get the B2 value, and then you can multiply it with the mean of x2 and you subtract B3, which is from the another formula, and you multiply it with x3, so that will give you B1. How you calculate B2? B2 can be calculated summation the x3 value square, then the sum of x2 into yi product being sum, then x2 x3 sum multiply with the sum of product of x3 and yi columns, and similarly being divided by summation x2 square, summation x3 square, and the product of summation x2 and x3. So now similarly you have a formula for B3 as well. So we already know these formulas, nothing new in it, it's the same old slide. So I'm just focusing on the formula of B3. I can use B1 and B2 as well, but just B3 is a bit more easy to have everything visible, so I will focus on B3. So let me start with the same model, B1, B2, B3, and let me show you how OLS method cannot be estimated when there is a perfect multicollinearity. This is the same formula of B3 which I show you on the previous slide. Let me start with assumption. I'm saying that x3 is equal to 12x2, or the age in year is equal to the age in month multiplied by 12. So let's make it the same. Yes, the value will be exactly the same in this case. So a case of perfect multicollinearity, and then the above formula which I'm going to have here, I'm going to replace x3 with 12x2, or I'm saying that these two are perfectly determined of one another, so I'm replacing x3 with 12x2, and we see what happens to this formula. So let me start with B3 is equal to, and then summation x2 square as it is. Instead of writing summation x3 yi, I will replace the x3 with 12x2, so that becomes summation 12x2, and yi come as it is, so yi, then minus, then summation x2, and then x3, so summation x2 I, x3 being replaced by 12x2i, so I will write 12x2i, then multiply with summation x2 yi. There is no x3 I term here, so I will not replace anything. Divided this whole with summation x2 I square, so it will come as it is. Then summation x3 I square, so I will take the square of 12x2i, so summation 12x2i whole square, then minus, and then summation x2 x3 whole square. So summation x2 is okay, x3 would be replaced by 12x2, so summation x2i and then multiply with 12x2i whole square. So all I did is replaced the x3i values with 12x2i, and I make it with a different color so that it's visible. Next we simplify this, so summation x2i come as it is. The 12 with the summation would come in the start because it's a constant, so this become 12 summation x2i yi, and then 12 could be brought at the start, so 12 summation x2i square come as it is, summation and then x2i yi. So I just bring that 12 at the start, minus, similarly I will bring that 12 here. So this is summation x2i multiply with x2i, so that make it summation x2i square, and then summation x2i and yi, and divided by, now summation x2i square, I would just write it, and then this 12, when I want to take it out, that become 144, 12 into 12 make it 124, so I will bring it at the start, summation x2i square, and then multiply with the summation x2i whole square. This x2i square and then x2i square, this multiply and this become x2i square whole square, minus 144, again the 12 become 144, and then summation x2 square whole square, x2 get multiplied, this become x2 square and its whole square. So that's what is written. Now look into it, look at the top values, it's the same values, 12 summation x2i square into summation x2yi minus the same term, so that make it equal to 0. And then look at the bottom or the denominator value, 144 summation x2 square whole square minus 144, again the same term, so divided by 0, and then make it B3 being equal to what? 0 divided by 0, what is equal to? It's infinity. It's undefined. So what does it indicate? B3 cannot be estimated. So we can do the same for B2, we can do the same for B1, and the conclusion from this is, what is the conclusion? The conclusion from this this particular slide is, if there is a perfect correlation between the two explanatory variable of a regression model, you cannot estimate the beta parameters because the OLS method break down, and we just saw that B3 cannot be determined. That can be short for B2 and for B1 as well. Please note, it's not for memorization. This derivation is not for memorization. This is just to tell you that why the ordinary least square method fall down when you are going to have a perfect multicollinearity in your data. So the conclusion is, in case of perfect multicollinearity, OLS estimator cannot be estimated. So let me go back to the slide from where I started. The consequences of multicollinearity. If there is a perfect collinearity, OLS estimator cannot be estimated. So now you know why. Because the procedure breakdown, you are unable to estimate the beta coefficients. So that's the case of perfect multicollinearity or perfect collinearity. So the conclusion is, when you have perfect collinearity in your data, you cannot apply OLS estimator. You are done. So that's the extreme case. Second, if collinearity is not perfect but high, then you can estimate the ordinary least square coefficient, but there will be some consequences to it. Now, we already started with the concept of having perfect collinearity and then imperfect collinearity. In perfect collinearity, no estimation possible. OLS method cannot be applied. You can say bye-bye OLS. But if it's a case of not perfect collinearity, you can apply OLS, but it will come with some consequences. So let's see what are these consequences. The first one is that OLS estimators are still blue. We already know what is blue. Best linear unbiased estimator. So if we apply OLS method in the presence of imperfect collinearity, the OLS estimator will be blue. Best linear unbiased estimator. Okay, if it's blue, what's the problem? The problem is that the standard error of the coefficients are larger compared to the case of no perfect collinearity. Now, what are the consequences? It makes the t-value small. Now, I'm sure you are lost. So let me demonstrate that. Again, the model, dependent variable, and two explanatory variable. You know that already, okay? So when we estimate these models, we get the small betas or the numerical values. Numerical values for beta 1, numerical value for beta 2, and numerical value for beta 3. Clear? The next, we calculate the t-values. How t-value is calculated? T-value is calculated by taking the numerical value. For example, we want to do it for beta 1. So we will take the numerical value of beta 1. We will divide it by the standard error of beta 1. Similarly, we want to calculate the t-value for beta 2. So we take beta 2 and we divide it by the standard error of beta 2, and then similarly for beta 3. Now, I didn't ask you ever to do that manually. We do it through the software. So let me show you the output of the software. So this is one of the output which we got in our previous classes. We regress output on the two variables, labor and capital, and we got their coefficient 233, 233, 1.6 for the constant, and then for the labor for 7.98 and for the capital 9.95 respectively. So these were the coefficients. Now we are saying that these are the coefficient, this beta 1, beta 2, and beta 3. So the coefficient. Now we want to calculate the t-values. So the t-values can be calculated by dividing b1, the numerical value of each coefficient, by their corresponding standard error. So from where we get the standard error, it's just the next column of the output of the regression which you run. So the standard error of the beta naught is, for the beta 1 is 1250364. For labor, the standard error is 7.058, and for the capital it's 0.978. So we take the standard error from this output and divide the coefficient with the standard error to get the t-values. So this 6.798 we obtain while dividing the labor 47.98 coefficient with its standard error 7.058, and similarly we took the 10.17 dividing 9.95 with 0.978. So now when there is multicollinearity, now coming back to the topic, you got a revision of what we have studied already. So now when there is a problem of multicollinearity, what happens? The standard error become larger. Now focus on the t value. What happens when the standard error become larger? When the standard error become larger, what do you get? The t value. When the denominator become the larger value, the t value will become smaller. When the t value becomes smaller, it has the consequences. What are the consequences? We already know that the t statistics are checked against the probability. So if the t value becomes smaller, as the case is for the constant here, it becomes statistically insignificant. So let me put it in words. When standard error become larger due to multicollinearity, now the consequence of multicollinearity, imperfect multicollinearity, is that the standard error become larger. So when the standard error become larger, the ratio of the coefficient, which is here, the ratio of the coefficient B1 to the standard error, which we call t value, that becomes smaller. When that ratio becomes smaller, it has a consequences. We get a t value which is smaller, and thus the chances of not rejecting H0 increases. So we may end up not rejecting a null hypothesis that technically should be rejected, or in another word, we will be making a wrong decisions. So let me explain it more quickly. When there is a problem of perfect multicollinearity, when there is a problem of perfect multicollinearity or perfect collinearity, OLS estimator cannot be estimated. We already saw why. And if multicollinearity is not perfect, but it is high, then the OLS estimator although are blue, but have a larger standard error. So when they have the larger standard error, their t value will become smaller, and when the t value becomes the smaller, we would not be able to make the correct decision, or we will not be able to reject H0 when it is supposed to be rejected. So that's one consequences. Larger standard error, and that causes us to have a smaller t values, and that causes us not reject H0 where it's supposed to be rejected. The second consequence of multicollinearity is that you get statistically insignificant coefficient despite of the fact that your regression model has a higher R-square value. So let's say you have a data, it has a problem of multicollinearity, you run the regression model. When you look into the R value would be high. But when you look into the individual statistical significance, you will find a lot of variable with not having statistically significance probability. So in another word, your model fit would be affected by the multicollinearity. Then one may conclude misleadingly that the true value of these coefficients are not different from 0. So ultimately you will be making wrong decision, as I told you, and you will be considering that a particular coefficient is statistically not significant or it's equal to 0, where it will not be. So we will be concluding the wrong decisions. Finally, two more things related to the consequences. First one is the regression coefficients are very sensitive to small changes in data, especially if the sample is relatively small. So what does it mean? It means if you increase the size of your sample, your coefficient will vary very rapidly. Let's say I have 100 observation and I run a regression model. So and then I increase the sample size to, let's say, 120 and 130, my coefficient will change dramatically. technically it should not be changed, but because of the multicollinearity, the variation in the betas for different sample size would be really big. So that will also because of due to the multicollinearity. And then one more, which is not mentioned in the book, but I will just quote it from my own experience and some study of other books, that when you have a problem of multicollinearity, the sign of the coefficient may comes as opposite to what you are expecting and what is your intuition. For example, you may be expecting that X is positively correlated with Y while formulating your economic model, but when you estimate that model and your data has multicollinearity, you would be getting negative value. So if you have one such case, it may also be an indication of or it may be the reasons that there is a problem of multicollinearity in your data. Okay, so now let me take you to EViews and let's talk about some practical way of looking into these things which we have studied in the previous half an hour or so. So the task which I'm going to give you, since we are not in the class anymore because of so many reasons, so let me give you a practical task which you can just try with having your EViews software. Please download the data multicollinearity table 4 from your LMS and check the data in the variables as in this given data. The data has a lot of variables. It's primarily we are interested to regress hours worked, which is measured in 1975. So that's the hour works by female, and we are going to regress it on the remaining 15 variables in this list. This list include age, which women age in years, then education, years of schooling, then the experience, that's the actual labor market experience measured in years, then the family income, that's FMINC, then the father education, the schooling of the father of the female worker, then the husband age, the husband education, then the husband hours worked during the years, then the husband wage during that years, then the family having kids of under age 6, and then the kids between age 6 and 18, then the wage being earned by the female worker, then the mother years of schooling, then the federal marginal tax rate for a woman, and finally the unemployment rate in the country of resident. So this is the data which is taken from a study which I didn't feel like to refer at this point. We don't need that. So the first thing which you should do is download this data, look into these variables, verify that you have these variables in your data, then think about what are you expecting in terms of the correlation among explanatory variables. So look into these variables, think that you are going to have a dependent variable, hours of work, and then the all independent variable, and think if any of these variable is linked with another variable. So since it's one way of teaching, I can't ask you here, so it's better I raise these questions myself, so and then answer it by myself as well. So for example, we can think of woman wage and her mother-father education. Think of it, for example, woman wage. Where is woman wage? It's here, wage. So the wage of a woman who work, is it going to link with her mother education or her father education? Think for a while. Let's say you have a data of working women and you have a data on their parents' education as well. Do you think it will be correlated? Well, to me, it may be, it may be not. But well, if you think a bit more longer, then you can think that, okay, if a father is educated and if a mother is educated, most probably the woman would be educated as well. And if a father is more educated and a mother is more educated, most probably the female, the daughter, would be more educated as well. So you see, there is a link. there is a link between the woman wage, because when a woman is more educated, she is expecting to be getting more salary or more wage or higher wage. So mother more educated, father more educated, and obviously the female more educated, and obviously the more wage. Similarly, woman wage, her husband working hours and education. When a husband is working for more hours, expectedly, that's the hours husband works, variable number 9. So if a woman husband is working for longer hour, most probably the female has to stay at home and take care of the children and household, so she may apparently be getting lesser time for work. So you see, you can think of all kind of relationship among these explanatory variables, and that's essentially the problem of multicollinearity. So now I would skip the theory to repeat all the things again. I would stick to what we are going to do, the practical part. So let me move to the next slide. We run the following model in which we have the dependent variable as hours. The hours the female is working, and then it's the function of age, education of the female, her experience, then the family income, then the father education, husband age, husband education, husband hours worked during that particular year, husband wage, then the kids under age, kids less than 6-year-old, kids between 6 and 18 years, and then wage of the female working, then the mother education, then the marginal tax rate of the government in which the country where she is working, and then the unemployment rate in the country. So this is the model you have to run, and you have to run a multiple regression model using hours as a dependent variable, as I just showed you, and the rest as an independent variable, and you have to report its EViews output. One additional thing which you have to do here is that you have to construct pairwise correlation matrix. Now, I have shown here how you can do that, but importantly, what is pairwise correlation matrix? I'm sure you have studied, well, you have you know the concept of correlation. I told you multiple times, and you have studied it in statistics too as well. When do regression analysis, we do construct correlation matrices while doing these analysis, and in these matrices we have all the explanatory variables. Let's say we construct a matrix in which we have all the explanatory variables, and we check the correlation among these. For example, we will see that how age is correlated with education, experience, and all these 14 variables. Similarly, we will see how the education is correlated with age and all these. So we construct a matrix of that. Why we do that? Because we want to see that how the explanatory variables are correlated with one another. Or in other words, we are going to see for a possible multicollinearity issue while constructing these correlation matrices. So how we can do that in EViews? In EViews, once you open all the variables in group, you go to the tab open on top of that group, you click on covariance analysis option, and then you tick only correlation and click OK. That will give you the correlation matrix. So let me demonstrate that, and let's then interpret the results. So let me go to EViews. It's a standard procedure we import the data, so I will leave that. So once you import the data, check the variables: age, education, experience, family income, father education, household age, husband age, husband education, husband hours worked by the female worker, husband wage, kids 6 and 18 years of age, kids less than 6 years, mother education, marginal tax rate in the country, unemployment, and wage. So we are going to run the regression model which we just discussed a while ago, which is shown here. And now I'm going to select first the dependent variable, so that then I don't have to reshuffle the thing. So first I will take hours, that was the dependent variable. it's going to be regressed on age, education and experience of the worker, then the family income, then the the father education, then the husband age, education and husband hours worked and husband wage, then the kids in the family less than 6 and between 6 and 18, then the mother education, then the marginal tax rate, then the unemployment, and finally the wage. I think the wage was somewhere in the middle, but well, it's okay, we can have it at the end as well. So I open these as a group first to create the group. Then I first go to proceed, make equation. I make sure that the dependent variable is hours, and all this, I take this C, I will cut it, I will put it at the start so that I get the constant as per the model. I check the wage is just before the mother education, so I would take the wage and I would paste it just before the mother education. So now I have all the variables which are required. I make sure that least square method is selected and the sample size, and I will press OK, and I got the coefficients of the model. I'm going to discuss this output shortly. The second thing was to look into to construct the correlation matrix. So for correlation matrix, first all the variables for which you want to calculate the correlation matrix should be open. So if you look into it, I have all the 16 variable, 15 explanatory variable being open in the group. I go to the view, then I go to correlation matrix where it is covariance analysis. So here is the covariance analysis. I click on this. So I got a new window which is called covariance analysis. Here are a number of options. For time being, I will ignore all. I will just click on correlation matrix. I will uncheck the covariance as well. So I'm just interested in correlation matrix, and I will press, will make sure all the sample is selected, and I press OK, and I got a correlation matrix. Where is it? So this is a correlation matrix. Now don't be scared by so many numbers. We are going to interpret that shortly as well on the slide. So let me now move to, so we got two things from here. First one was the output of the regression, and the second is the correlation matrix. So let me switch to the slides. Wait, I have this output. I would advise strongly before moving further with this video, it's better that you first do this in your EViews and have this output. So once you have this, take 10 minutes, 15 minutes or 5 minutes, depends how good you are with EViews by this stage now. So once you have the output, this was the model and the output. So this was the output which I got. A quick look into it. We see that the dependent variable was hours, and then the coefficients values are given, the standard errors are given. So now you know how the t values comes. T values is coefficient divided by the standard error, respective ones. So you put the t values, and then you see the probability values. So observations. So do you see anything? Any problem with this model? Yes, take your time. Look into the coefficient of age. What's wrong? Oh, its value is greater than 0.05, so statistically not significant, or technically it's equal to 0. Oh, look at this one, education, statistically not significant. Look at this one, further education, statistically not significant again. Look at the husband wage, and similarly some more. So number of observations. First, model is significant overall. So look at the F statistic. Well, 14.09655. It's statistically significant, but not too much. Look at the R square value, 0.339. Well, it's explaining 33.9% of the total variation in hours. All these explanatory variables are explaining only 33.91% of the variation in hours. So the question is it a good fit? Is this R-square value is high? Well, you people have been using time series data and you have been more oftenly seeing the value of 0.9 or above, so you may think that it is very low, but trust me, for cross-sectional data 0.33 is very high value. So well, R-square value 0.339 for micro data is not that bad fit. And then look at the standard error t values and the probability values of the coefficient that are not significant. So we already saw that number of variables, although we have overall not that bad fit with a not so low value of R square, given that it's a micro data. We have a lot of statistically insignificant coefficients. So these are insignificant because we have higher standard error for these variables. For example, education is statistically not significant, and you see that standard error is very high and it's higher than the coefficient. And similarly, you can see another one, standard error of other education being higher and even higher than the coefficient. So that's the reason you are getting a lower value of t statistics, which I told you a while ago that when you have a multicollinearity, you get a higher standard error value that result in a higher denominator of the t ratio, t statistics, which is calculated by dividing the standard the coefficient with the standard error. So a higher standard error value mean a lower t statistic value, and ultimately an insignificant value for the probability, and thus rejecting the entire coefficient being equal to 0 where it may not be. So that's the consequences of the this particular reasons we can think of having issues with multicollinearity. Then keep these results and data handy throughout this lecture, and for sure in the next lecture we are going to discuss this output again. So keep this data handy, we are going to need that for the next lecture as well. Next, the correlation matrix. So what is this correlation matrix? This correlation matrix tells you, let me go one by one. So if I take the first value, what does it show? It shows that age correlated with age, it's 1. The correlation between age to itself is 1. Why it's 1? Because both moves perfectly together. Now experience with age is 0.483. So that's the correlation coefficient between age and experience. Similarly, experience with experience is 1. Then education with age is minus 0.52. Then education with experience is minus 0.0152. And then education with education is 1. So what you can observe is that the diagonal term is 1 for the entire, let me point it out, these diagonal, these are all 1. So you can see these all. So these diagonal terms are all 1. So this diagonal term shows the correlation of the variable to itself, and the rest is with the other variable. So this is the correlation matrix. So some observation, we have to check if there is some high correlation among certain variables. Well, apparently this is not very good visible, but we can see some value, some higher value. Now we have to define what is high, what we mean by high correlation. What is high correlation? Is 0.5 a high, or is 0.98 is high? For that you first need to know that what is the plausible limit between what is the value of the correlation, or what is the values, possible values of the correlation. We already know that the correlation coefficient value range between -1 and +1. We already know that. -1 happens when two variables are perfectly negatively correlated, and +1 happens when two variables are perfectly positive correlated. So any value close to -1 or +1 is high correlation. So that's what I've written here. higher close to -1 or +1, but we set a range of 0.5. So 0.5, any value above 0.5 positive or minus 0.5 will be considered as perfectly, these will be considered as highly correlated values, and we would suspect the strong correlation, or in another word, multicollinearity issue between these variables for which the coefficients are higher than 0.5. So if there exist any such values, we may suspect that there is a problem of multicollinearity in our data. That's it for today. See you tomorrow in new lecture. Meanwhile, if you have any questions, please do post it, or email me, or you can post it below in comments. I will like to answer. We will continue this discussion in next lecture. Thank you for your time and patience. Thanks.